Well, thank you. Thank you for the introduction and also the opportunity to be with you at this annual meeting of PM and to report on a project we've just completed at UNR on the design, fabrication and commissioning of a large laminar soil box and its own shake table. So why would we want to do this? Why would we want to invest 5-7 years of effort to in fact build a laminar soil box? And at the highest level is to experimentally gain insight into soil structure interaction during earthquakes in structures with deep foundations and with or without nonlinear soils, well, with linear or nonlinear soils. And then to use the facility to validate numerical tools that are out there for SSI, such as Lush and SASE and Alistine and OpenSeas and Real Easy, and the list goes on. But doing soil structure interaction experiments are really not feasible at full scale. The properties of nonlinear soils and structures are difficult to model in laboratory scale experiments. Nevertheless, most laboratory approaches for scaled experiments use one of two approaches. And the first, as already been mentioned in the previous talk, is to use a geotechnical centrifuge with an in-flight shaker. The confining stresses in the soil are correct, but embedded structures are at very small scale, say 1 to 40. And as a consequence, from a structural response point of view, the scale or the small scale is a disadvantage. On the other hand, if we use a laminar soil box on a shake table, where the structure scale can be much larger, say 1 to 5 in a big box, the confining stresses in the soil are not correct. Really, the path forward is probably to use both approaches in a hybrid fashion. But the number of large laminar soil boxes in the world are really quite few. So if you are not familiar with the intent behind a laminar soil box, let's think in the upper part of this slide of an infinite half space subject to ground motion coming in from the base, with the structure here shown in a tan-colored box, a box which is infilled with a tan color. And then under shaking we get pure shear deformation in our uniform half space and interaction between the structure and the soil. Now we want to replicate the field conditions in the laboratory, so we take an island out of the field and put it on a shake table. And then the conundrum is how you keep the soil on the table in a box without any way restraining or stiffening or changing the properties of the soil. So here in this cartoon in the lower part of the slide, the box should be invisible to the soil, but keep it on the table. And so the walls of the box are usually a stack of laminates which can move over each other to allow the replication of shear deformation as in the free field soil. So this is definitely feasible and it's been done, and indeed UC San Diego, as we've just heard, has 1 or 2 of these large boxes in the LH Post facility. So the errors that come through a laminar soil box, because we are working at 1G and therefore we don't have the true confining stresses in a scaled amount of soil, our approach is to build the largest soil box and table that we can possibly afford, because that will minimize the errors due to low confinement stresses. Not to attempt to satisfy scaling laws for soil and embedded structures such as unit weight, strength, moduli, inertia forces, but to use actual soils and structural materials and study SSI experimentally in the box soil system, so at scale. Then validate numerical codes using data from these experiments at that scale, and when having confidence in the numerical models, use those validated codes to scale up to prototype structures and soils. The same technique gets used in fluid structure interaction, so we're not the first to use it, but FSI has the similar issues as SSI working at scale in a laboratory. So the 4 key decisions, having decided to build one of these boxes, is should the box be mounted on a general purpose shake table or on a dedicated platform. A platform designed just for the soil box and not one that's used for both soil excitation but also structural excitation. And we have multiple shake tables at UNR which could be used to support a soil box. But the question was whether to build another one, just the soil box. Should the box have rigid walls, or should they be laminar, i.e. shear flexible? And there are a good number of rigid boxes out there, and they're a great deal easier to design. Should the box be excitable uniaxially or biaxially? So is this a uniaxial box shaking in one direction or a biaxial, which should be two components, north-south, east-west? And should it be conventional or smart? Should it be a conventional box or a smart box? And by a smart box, I mean a laminar box which has actuators up in the walls of the box, which help maximize the area of pure shear deformation in the soil and minimizes the interference of the walls of the box on the behavior of the soil. So we went with a dedicated platform. It's a laminar box. It has biaxial capabilities. And it's a conventional box in the sense that we do not have actuators up in the walls of the box. We wanted to achieve soil yield, so somewhere with a shear strain of 1 to 2%, be able to develop structure yield, have soil gapping between the structure and the soil surrounding it, or allow for or be able to study structure sliding within the soil. We needed to satisfy physical limitations of available laboratory space. So we had a volume about 60 feet long, 40 feet wide, and 30 feet tall as the envelope for the box into which we needed to fit the box, the platen or shake table, the actuators, the reaction buttresses. And then the other physical constraint is the reactive mass. The foundation of the laboratory is reactive mass to which the actuators must be connected or reacted against. And this particular laboratory that was available to us had a foundation mass of around 3,600 tons. Then the fourth constraint on this slide is one we all get faced with every day, is the budget, the available funding to get this done. So the shake table features are on this slide. The picture to the left shows half the number of actuators used to drive the platen there. The platen is a low weight, high stiffness, 24 foot square by 4 foot deep steel egg crate, fabricated in 9 different modules and welded together in tight tolerances within the laboratory. Now they've been assembled in the laboratory, the only way to get the platen out of the lab is to take to it with a gas torch and cut it up. But it came into the lab in 9 separate modules and welded together on site. The actuators, there are 8 110-ton servo-controlled actuators in a chevron configuration to excite the platen in both north-south and east-west directions simultaneously. And they're sized to yield 350 tons of soil, although their payload capacity is up around 500 tons at 1G acceleration. The platen itself sits on hydrostatic bearings, which are slide bearings on a thin film of oil. There are 8 of them, and they're actually vertical actuators, but with very limited vertical stroke. Overturning resistance is taken out by 8 tie-down struts around the perimeter of the platen. And then there are blowdowns, like we were hearing at San Diego's facility. We also have blowdown accumulators to give us additional hydraulic power. We have 2 sets of these in the basement underneath the table for earthquake motions with very high energy content. Then moving to the soil box features, which are the heart of the matter. The soil box is alternating layers of steel hollow sections and elastomeric bearings. Elastomeric bearings are inherently more robust than mechanical or steel bearings, which are inserted between the individual laminates. They're able to take a lot of punishment, large deformations, which may occur should we get local failure in the soil. Much more superior. The big boxes that exist in the world are in Asia, and all of them that I'm aware of have all been damaged during use They all use mechanical bearings, and the mechanical bearings have been damaged, limiting the capacity of those tables. This, we believe, is the first time that elastomeric bearings have been used for this purpose, certainly in the United States and perhaps worldwide. And there's a sketch on the right showing 3 elastomeric bearings between the steel laminates. The box wall needs to provide for complementary shear through friction with the soil and transfer those loads to the table platen below. As a consequence, the box wall is under alternating cycles of compression and tension due to reversing loads during an earthquake. And this puts the bearings in reversal loads of compression and tension, which makes the design of the bearings tricky because rubber doesn't do well in tension. A whole separate story on getting that right. We also need faceplates to attach to the box frames to mobilize the soil and shear, and the gap between the faceplates have to be sealed to keep the soil in the box and prevent soil spillage. Some of the details for transferring shear from the soil into the base is shown in the middle of this slide. Steel angles have been welded to the base plate around which the box is assembled, and then the walls of the box glued layer sheets have been glued to the faceplates. And the white strips you see on the right are in fact the seal between the faceplates that prevents soil spillage or soil escaping from the box itself. So overall dimensions, it's an octagonal box. It's not rectangular, it's not square, and it's not circular. It's an octagon, and we can talk later if you wish as to how we got to an octagon. The major dimension is a little under 22 feet, a little over 21. It can be assembled to any height that you wish in 10-inch increments. But the maximum height would be 3 5-foot segments around 15 feet, as shown in the cartoon on the right. The interframe connectivity is elastomeric bearings. They're interchangeable with a number and stiffness, so we can change the stiffness of the box walls as needed, depending on the properties of the soil that are to be researched. Biaxial excitation, the fundamental frequency of the empty box is around 1.5 hertz. We believe the footprint of any embedded structure in this box would be around 5 feet. So depending on the prototype dimensions, one can back out a scale. Maximum soil strain is 15%, which is way beyond the yield strains in soil, and this, in this case, is limited by the physical constraints of the box wall. The weight of the box itself is around 50 or 60 tons above the first layer of soil. The weight of soil at a density of around 120 pounds a cubic foot is around 350 tons. So these are 2 images of the completed box. The one on the left is on the floor of the laboratory, with one of the fabricators alongside of it, assemblers alongside of it for scale, and then on the right we show the box on its platen, the 15-foot tall version. You can see in the foreground concrete buttresses which are pre-stressed to the floor of the laboratory, and 4 actuators in a chevron configuration at this south end of the box, and a similar number of actuators on the opposite end, the north end of the box. So this is, this is shaking the box without soil. Remember, there's no soil in this box. So we wanted to get the properties of the box as without soil to help with numerical modeling and simulation. And these are the frequencies of 5 modes that we determined with white noise. There's the calculated numbers based on our numerical modeling and the measured numbers on the right. Elastomeric bearings, all rubber materials, have stiffnesses that are strain dependent. So we have results here at different strains or different levels of excitation. But the first mode's around 2 hertz. And the fifth mode is around 10 or 11 hertz, empty. Then when it comes to filling the box, to commission it with soil, we brought in 13 dump trucks of soil stacked in the background, and then with the front end loader moved 3 to 4 yards into a hopper, which is shown here. This hopper is then lifted over the soil box. It has doors that open from below using hydraulic actuators to dump soil into the box itself, which then need to be compacted to the desired density or specific weight. So we did this for a 10-foot box, saved time, and shook it in the both the X and Y direction using L-centric ground motions. And this video that I could show you at 0.78 G input accelerations show just rigid body motion. It's nowhere near as flexible. The natural period pull of soil is around 10 hertz. But in the interest of time, I will move on to the results from doing this. So this is a strain profile. Shear strains calculated from the relative displacements of all the laminates down through the box. There are 20 of those to give us the strain, relative displacements, and therefore average strain across the width of the box. And we can see here that at high accelerations, high input ground motions or table motions, we're out between 1% and 2% strain in the soil. So we're happy with this, that we are indeed able to yield soil in this box. A project like this is dependent on a large number of people working together. We had an advisory group, I'll say the UNR advisory group, built up of structures and geotechnical academics. We had the laboratory personnel that worked on the table itself. Patrick Laplace did the table platen, the hydraulics, and assisted with commissioning. Sharif Alfas, my co-presenter, designed the box and helped with commissioning. And technicians, Chad and Todd Little, helped across all different fields and aspects of the table. Graduate assistants did numerical modeling and assisted with soil handling, instrumentation, data reduction. And our sponsors are the Department of Energy, project lead David McKellen on behalf of the Lawrence Berkeley Lab. And the University of Nevada also contributed to the box with in-kind contributions. We had an external advisory board, some of whom are in the room today, and we certainly appreciate the guidance you gave us during the early part of the design and conceptual work on the box. And we have collaborators, and I'd call out Boris Jimrich at the UC Davis and Jenna Wong at San Francisco State that helped us again during the numerical modeling and design concepts.